Good morning, good day, or good afternoon, wherever you join us today. Welcome to our webcast, Speed Up Mission Critical Heterogeneous SoC Development with PikeOS and TRACE32. This webcast is provided to you by SYSGO and our valued partner Lauterbach, a leader in embedded software development tools. Lauterbach and SYSGO have teamed up in order to present a complete software solution for the safety critical markets from debut to deploy. My name is Franz Walkenbach, and I'm glad to be your moderator today. So I would like to present Armani Kashud. Armani is the Technical Product Marketing Manager at SYSGO. She has a strong background in data science, industrial engineering, and edge technologies. She joined SYSGO in July 2023 and has a degree in industrial engineering. Also, we have our guest Rudolf Dienstbeck, system engineer at Lauterbach. Rudolf is an expert on debugging of real-time operating systems and hypervisor environments. He joined Lauterbach in 1995 and graduated in computer science. Let me go through the agenda items per today. So first we do some company introductions of both companies. Then we have PikeOS and PikeOS for MPU for mixed criticality. Then Lauterbach will take over to present TRACE32 and debugging on heterogeneous SoCs. Then we will have a live demonstration and then a conclusion and the question and answers at the end. With that, I would hand over to Armani.
Good morning, everyone. So let's start by presenting first SYSGO as a business. SYSGO stands as the leading European operating system vendor for embedded systems. Our primary mission is to be a reliable partner, ensuring that our clients receive safe and secure technologies, paving the way for high-end software solutions that integrate seamlessly with any IoT device across the globe. We also provide board support packages, certification kits, and professional services, including product training and consulting. Our legacy dates back to 1991, giving us over 3 decades of experience, especially in the certification of safety critical systems. In 2012, SYSGO became part of Thales Group, and we do operate globally, and we do have local presence in Germany, France, Czech Republic, and the UK. In SYSGO, we are committed to provide products that have been designed to meet the highest requirements when it comes to safety and security, including PikeOS, first released in 2003, which is a Type 1 hypervisor and a hard real-time operating system based on separation kernel. AlienOS, our first product, an industrial Linux distribution with long-term support. And more recently, PikeOS for MPU that is compatible with lightweight systems that comes with a memory protection unit MPU only, which provides real-time partitioning for MPU architecture. At SYSGO, our commitment extends beyond products. For this, we are dedicated for delivering a comprehensive client experience, including guiding product development with focus on system architecture and security, streamlining hardware integration for optimal performance, offering enduring customer support post-development, and providing tools and services for the entire product lifecycle.
Okay, thanks, Armani. Welcome, ladies and gentlemen, also from my side. Let me introduce Lauterbach in a short presentation. Our mission, as you can see at the top, is really enabling embedded innovations, and we really take this seriously. Lauterbach was established in 1979, at that time by Lothar Lauterbach, hence the name of the company. At that time, he started with the first debugging tool called TRACE32 on the famous Z80 microprocessor. Then Later came TRACE32, first starting with 68K processors, and then developed to all these different architectures. So today we are really the worldwide leader in debug and trace tools with more than 140,000 installed debuggers, more than 10,000 customers, and a market share about 40% in debug and trace tools. The most important information, I think, is that we support more than 150 architectures, and from the architectures, more than 10,000 chips that we maintain in our database. So the products of Lauterbach are mainly debug solutions in a modular and flexible way. So the main product is the TRACE32 debugger, a hardware debug solution for, as I mentioned, more than 150 microprocessor architectures, and for all kinds of hardware debug interfaces. Alongside, we do have high-speed trace extensions for almost every available trace protocol on the market, so that you can do a real-time tracing on your targets without having any impact into a runtime. Accompanying with our hardware tools is a feature-rich software suite called PowerView, which acts as the software, debug software for our tools, doing all the debugging and performance analysis and trace analysis, whatever you need. And it acts also as a standalone software debugger, for example, with an own instruction set simulator, or as a front end for emulation systems, like, for example, QEMU or other emulation systems.
Now move on to SYSGO's main product, PikeOS. And here we will dive into PikeOS's architecture, and we will explore how its sophisticated design addresses the challenges of safety-critical systems. It's essential to highlight that PikeOS adopts a modular approach, facilitating the smooth integration of varied software components. This capability enables the crafting of customized solutions, aligning perfectly with the unique needs and requirements of different applications. As we can see in this slide, on the lower level of PikeOS, we find the PikeOS microkernel, which consists of a generic part, a CPU architecture-dependent part called ASP, or Architecture Support Package, and a platform-dependent part called PSP, or Platform Support Package. On top of that, and in the user mode level, we have the PikeOS system software component, which is the first user space application launched by the PikeOS microkernel. It is responsible for initializing partitioning, inter-partition communication, and health monitoring. On top of the core operating system, there we can find the different partitioners. In this context, we often refer to software partitioners as virtual machines due to their ability to host an entire guest operating system. This allows each partition to operate independently from the others. And here, PikeOS supports multiple guest operating systems, including POSIX, ARINC653, Linux, Android, LinOS, PikeOS Native, and many more. PikeOS partitioners showcase its capability in effectively handling mixed criticality applications. By isolating software functions, it enables different applications from safety-critical to non-critical to run securely on the same platform. This positions PikeOS as a trusted choice for sectors that needs both safety compliance and versatile application integration. And this will allow industries to minimize certification processes, address licensing challenges through separation, and to facilitate the incorporation of legacy code. In this context, we are ensuring the support of mixed criticality applications by using two main security mechanisms, which are resource partitioning and time partitioning. So in resource partitioning, we are ensuring that every partition in PikeOS has its own dedicated set of resources. By doing this, we are enforcing strict isolation between partitioners, preventing one partition from accessing the resources allocated to another. Here is the MMU role to enforce memory isolation, and that contributes to the overall resource partitioning strategy of PikeOS, preventing any unauthorized memory access between partitioners. Time partitioning is also one of the security mechanisms to support mixed criticality applications. PikeOS ensures time partitioning by employing a real-time scheduler within its microkernel architecture. Each partition is allocated a specific portion of CPU time and priority, which the scheduler enforces. This guarantees that partitioners receive their allocated CPU time, preventing one partition from monopolizing resources. Progressing from our discussion on PikeOS's management of mixed criticality via partitioners, and let's transition to a notable update. SYSGO, the driving force behind PikeOS, has taken a significant step forward by integrating multi-core handling into their time partitioning mechanism. This improvement promises to redefine the realm of real-time operating systems, addressing the growing demands of today's complex embedded systems. However, safety issues regarding to multi-core systems may arise on software and hardware level. For this, SYSGO proactively implemented solutions to address those challenges. On software application levels, SYSGO has prepared all means for the user to define and implement an airworthiness architecture on the base of PikeOS. On operating system level, SYSGO has implemented all safety measures in order to safely set up mixed critical systems using resource partitioning, time partitioning, and fine-grained locking. And by the way, PikeOS is the first operating system that achieved a multi-core certification on SAIL4, which stands for the highest level of safety in the railway system. So continuing on the multi-core context, here hardware might cause further interference through shared caches. The good thing is that those effects can be mitigated by means of software measures, like cache partitioning and cache invalidation. And when using PikeOS, customers are enabled to build CAS32A compliant systems. To understand how this is working, let's have a look at this example. Here we have two cores in the time partition window TO1, where we run a non-critical partition and an application with a high impact on the cache. Afterwards, we are doing a cache invalidation, and then we run the critical applications in parallel. And from those, we know the exact behavior, because those have been certified and investigated so they don't access the bandwidth or the shared resources in an unwanted way. That way, we don't have any interference between those applications at runtime. After discussing PikeOS's multi-core handling capabilities, let's dive deeper into a specialized version of PikeOS, introducing PikeOS for MPU. PikeOS for MPU is a real-time operating system designed for the highest level of safety and security. It has the capability to execute concurrently applications with different safety and security assurance level. And here, of course, we are supporting mixed criticality. It has spatial and time partitioning, and PikeOS for MPU shares with PikeOS the same native API, the same customer development environment, which is Codeo, the same SYSGO development and test environment, the same qualification processes, and both operating systems share about 80% of the same code. And for the existing source code that you have, you can easily port it from PikeOS to PikeOS for MPU easily. Due to the nature of not having an MMU, the virtual address management and the ability to run a Linux operating system, of course, is not present within PikeOS for MPU. But it has address space protection, of course, thread management and scheduling, resource management and protection with respect to resource and processing times, health monitoring, inter-partition communication and synchronization, as well as intra-partition communication and synchronization, and I/O device abstraction and access control. Also, it has AMP multi-core processor support. So now let's explore the key differences between MMU and MPU. MMU, or Memory Management Unit, manages memory in computer systems, handling tasks like translating virtual memory addresses to physical memory addresses, paging mechanisms, and memory isolation. These functions are beneficial in larger systems that prioritize efficient memory usage and process isolation. On the flip side, MPU, or Memory Protection Unit, focuses on memory protection and access control. It establishes specific memory regions with set access permissions, ensuring only approved processes can access certain memory parts. MPUs are essential in systems where security and controlled access are paramount. In summary, MMUs are optimized for larger systems, needing memory translation and multitasking, while MPUs prioritize memory protection in simpler systems. MMUs enhance system performance by facilitating virtual memory and multitasking, and meanwhile, MPUs maintain security by keeping processes within their designated memory, safeguarding it against unwanted or unauthorized access. So now let's briefly summarize the pros and cons of the usage of MPU. So for the advantages, the usage of MPU allows for a tighter bound of worst-case execution time analysis, and thus higher time determinism. And also MPU runs on less complex hardware and chip design. And for the disadvantages of the usage of MPU, we have less flexibility on memory allocation, and the virtualization is not supported, and thus complex operating systems such as Linux cannot be executed here. So now let's get into the setup of MMU and MPU by separation kernel. MMU systems usually provide cache coherency and prefer SMP configurations due to higher efficiency in terms of memory usage and computing bandwidth. SMP systems can only handle cores of same types. For example, a mixture of MMU cores and MPU cores is not possible here. MPU hardware typically is less complex and does not provide cache coherency amongst the cores. SMP systems are possible with caches being switched off. However, this is disregarded due to the lack of performance. And here, it's worth noting that the MPU facilitates AMP systems by allowing multiple independent applications to run concurrently, each within its designated memory region. Since PikeOS and PikeOS for MPU have identical APIs and are running under the same development platform, Codeo, this allows simply to move tasks from one operating system to another one. And by using the same API, we are able to reduce significantly the learning curve, as you can just apply the knowledge that you got from PikeOS. So when it comes to development, we have our own development IDE called Codeo, which is an Eclipse-based IDE. Codeo is an integrated development environment for embedded systems. It has a quick and easy target system configuration. It has templates for system configuration and application development. Its simulation target is based on QEMU. It has target system monitor and target system tracing. It is fully featured for remote debugging, and it is available for Linux and Windows hosts. When it comes to certification, we do support all major safety standards, including avionics, railway, and automotive. And SYSGO has a very long history in certification projects, and almost every engineer of our team has been involved in such a certification project, whether it's safety or security related. And some of our reference certification customers are Airbus, Rockwell Collins, and Rheinmetall. In this slide, you can see the PikeOS components and their certification state. So you can see that the microkernel is fully certifiable, which means you can provide all necessary documentation, including traceability and coverage. However, if you have your custom board, the PSP needs to be developed together with you as customer. When it comes to operating systems and certifiable APIs, we have certifiable POSIX, and of course, the PikeOS native is pre-certified. And depending on your needs, we can certify further operating systems. In addition to that, for PikeOS, we also provide a certifiable file system and a certifiable UDP stack. Another important topic when it comes to certification is the tool qualification. So basically, you can do a certification without any tools being qualified, as long as you verify your results. And if you do that on a binary basis, it is basically possible, but very, very tedious. Therefore, SYSGO has qualified the major tools, for example, the ROM image builder and the VMIT builder. And here the VMIT stands for the Virtual Machine Initialization Table, and it is responsible for the configuration of the virtual machines. Both of those tools read the configuration file in XML and convert it to a binary. And since those tools are qualified, you can easily do the validation on source code level, which means you can quickly incorporate changes without doing the complete revalidation on binary level. So what also you can do with PikeOS and PikeOS for MPU is to run them on the same hardware platform. For example, today we have the Xilinx Ultrascale board here. And this allows to run PikeOS implementation on the Cortex A53 processor cores, as well as PikeOS for MPU on the Cortex R5 cores. Here, the single Codeo workspace simplifies development by consolidating all tools and interfaces into one platform. And the common native API ensures smooth application distribution, whether you are using SMP or AMP, offering both adaptability and efficient deployment. So in short, PikeOS and PikeOS for MPU offer a seamless and adaptable platform for optimal performance on heterogeneous SoCs. So to make it more practical, let's have a look to where we are interfering in the avionics domain. And let's specify what applications we can run on top of PikeOS and on top of PikeOS for MPU. As you can see in this slide, on the left side, we have PikeOS running on the Cortex A53, designed for high critical and complex multitasking applications. And here's what it covers. For example, here we can run flight management systems, integrated modular avionics, which provides shared resources for various applications to utilize it efficiently. Cockpit display this system is. And lastly, avionic communication. Now on the right side, we are looking at PikeOS for MPU operating on the Cortex R5. This variant is also for high critical applications, and it focuses on less complex but highly streamlined tasks. So it can run applications such as engine control units, stability augmentation, environmental control application, and also basic health monitoring application. The system basically checks and ensures the overall health of different aircraft components. So in summary, while PikeOS on Cortex A53 is tailored for complex multitasking needs, PikeOS for MPU on Cortex R5 is optimized for streamlined and safety-critical tasks.
So thanks, Amani, for the introduction to PikeOS, and let me continue in introducing our TRACE32 tools, and especially what they can do to help you in debugging PikeOS systems. So we already saw that we provide hardware debug tools, which provide stop mode debugging, mainly based on just the JTAG interface, so on a dedicated chip interface. Also, the TRACE32 trace tools are hardware-based, dedicated to a chip interface, usually ARM ETM, PowerPC Nexus, something like that. And they do a non-intrusive program flow tracing. And well, TRACE32 supports all architectures that PikeOS also supports, mainly ARM, Cortex-A, Cortex-R, on 32-bit and 64-bit, of course. Also Intel x86, and PowerPC 32-bit and 64-bit. And upcoming also the RISC-V chip. So accompanying our tools is our uniform graphical user interface for all of our products. It's really designed to get the best out of our tools. And it has the same look and feel for all architectures. It's command line based, but a feature-rich GUI. So command line based means it has a powerful scripting and based on practice commands and on Python. And it provides a headless mode, especially interesting for continuous testing environments. It has a special core and architecture support for peripheral view. It provides views for SMP debugging and AMP debugging, which we will see later. And it gives you performance analysis and access to code coverage and much, much more. So let me tell you a little bit about stop mode debugging versus run mode debugging. First, you may notice what we call run mode debugging, which means the debugger communicates with a debug agent on the target, typically a GDB talking to a GDB server. It needs an active interface, of course, and the debug agent needs to be active. So the target needs to keep running, so you cannot do any interrupt debugging, you cannot do any post-mortem debugging, and the operating system is usually invisible to the debugger. But this is best solution for debugging processes, debugging applications. If you need to concentrate on one application, just this debug solution is fine. So in contrary, the so-called stop mode debugging is our hardware-based solution, which is based on the dedicated debug interface JTAG. The debugger has full control over the CPU, and there is no need for extra software on the target, no target debug agent. If you're halting the CPU, you halt the complete system, including tasks, interrupts, whatever runs on your target. Everything is halted. So that means we have access to the CPU. We see what the CPU sees. That also means we sometimes have to fiddle a little bit around with the MMU context to also see other tasks that are currently not in the vision of the CPU. So you can debug actually everything. The startup code, interrupts, drivers, processor threads, communications. So everything what runs on your target. And you can do post-mortem debugging, for example, setting a breakpoint on a panic routine, and as soon as your software panics, you can see where it came from and evaluate why it ran into the panic. So let me tell you a little bit about functional safety, especially about DO178. So with our tools, you can do performance analysis on all levels like thread, functions, on source code level, and also on object code level. The same for code coverage, which is also provided on all levels, especially source code and object code level. And we are providing coverage up to MCDC. MCDC means modified condition decision coverage, where you have to cover all the decisions within an if statement and all the different paths that go along within a decision. And for the code coverage, we have also collaboration with external tools, which means you can export our code coverage to tools that, for example, do code coverage against requirement analysis. Regarding unit tests, you can do a manual setup with our TRACE32 scripting, or you can also do the unit tests with external tools, which provide automated unit tests. And we do have collaborations with all unit test tools out there in the world. Lauterbach provides a so-called TRACE32 tool qualification support kit, which allows to qualify TRACE32 within your tool environment and streamlines the tool qualification in your environment. So how do we support the Xilinx Ultrascale Plus, which we will showcase today? Of course, we support the Cortex A cluster as SMP or AMP, which means symmetric multi-core processing or asymmetric multi-core processing. We support, of course, the Cortex R cluster on this chip. We support the tracing of program flow, either on chip, which means you are tracing into the RAM of the target memory, or off chip, tracing into our own pools, which means saving RAM for your target. And you can do a synchronized development. So you can debug the A cluster and the Cortex R cluster at the same time, same for the trace, which we will see later. So which PikeOS versions do we support? Well, almost every version out there. TRACE32 supports PikeOS since version 3.x, now of course up to 5.x. We support the personalities for POSIX, for Apex, and for Linux. And we also support the PikeOS hypervisor, which is not part of the webinar today, just to mention it. TRACE32 also supports now, of course, PikeOS for MPU in the version 1.x, and we will see that later how that works. And let me mention that SYSGO and Lauterbach have a close cooperation, which really ensures compatibility between TRACE32 and all new future PikeOS versions as soon as they are released. So what can we provide when debugging PikeOS systems? I go through that quickly because you will see that in the live session. So you can debug the PikeOS kernel, which is of course usually not necessary, but you can debug the startup routines in physical, you can debug everything in virtual mapping, you can debug multiple tasks simultaneously in stop mode, which means no target agent is involved. You can inspect the call stack of waiting threads. You can debug interrupts, exceptions, kernel drivers, PSP drivers, really everything that's in your target. So we support displaying of kernel resources, tasks, threads, and all that stuff. We support the thread stack coverage if you need that, the thread context display, of course, thread related breakpoints, which means you can set breakpoints that only hit on a specific thread. There is a symbol management included, which supports you in handling the symbols of various applications and processes, and thread performance measurement. And yeah, already mentioned that you can debug drivers and user spaces simultaneously. Alongside comes the MMU support, because the core usually only sees one process, so that we can really look into all processes. We have a so-called MMU support. The debugger knows the target MMU and does all the MMU table box itself, so that the debugger can really access everything on the target, also in virtual address space. And of course, we have an SMP support, which means that all cores are started and released simultaneously, and you usually don't care about which core holds on the breakpoint. We automatically switch to that core that holds at the breakpoint. So then we provide the real-time trace using hardware trace-based streams, recording the program flow. So you can see the program flow history. We do provide a so-called context tracking system, which gives you ability to debug back in time. You can do, of course, then a performance analysis on drivers, threads, functions, and measure the run times of functions and do some charts and statistics. And out of this trace, we do the code coverage on the whole system, which is, of course, necessary for the certification, which we talked already about. And all that books without any target agents, which means no impact to the target. So in the upcoming live demo, we will show you a PikeOS Architecture SMP version on the Cortex-A cluster and a PikeOS for MPU on the Cortex-R5. We will use the board Alta96 from FNet, which has an Xilinx Ultrascale Plus on board. It will be an AMP session. We'll have 2 PowerView sessions, but you will see that right now in a minute. And that's how the hardware looks like. And with this, I would like to switch to my live demo. Okay, let's start our live demo and start the debugger, which I'm going to start right now. And the debugger will start up. And as soon as the debugger starts up, I can actually load the first demo, and simply by doing file run script, and of course I prepared a small script, which then starts our demo. Now the debugger already loads PikeOS into the target. It starts target on the Cortex-A cluster. The script automatically starts up the second TRACE32 session, which is tied to the Cortex-R chip, and also starts PikeOS MPU on the Cortex-R, and we are already up and running. So on the left side, you see TRACE32 for the Cortex-A. You can see this on the headline. On the right side, you can see TRACE32 for the Cortex-R5. So let's simply break our system, and you see that it automatically breaks both systems, Cortex-A and Cortex-R, so both are synchronized in debugging. You see hashed lines here. This is because we hold it inside the kernel, and of course I don't have the kernel source code, so this is just showing that we don't have the source code of the kernel. But you can already see in the status line, we have here halted within the sender application, and on Cortex-R we are halted at the bouncer application. And let's have a first look into the display functions. Here you can see the task list of the Cortex-A, so having several tasks, and also, of course, the same, you can open simultaneously the task list of the Cortex-R. Let's close these windows and shift these down. And you can also have a look into the threads. So these are all the threads running on your target. And not only that, of course, you can also look into the kernel drivers. So which kernel drivers are active in your system? And these are all things then that you can debug within your system. So I told you a little bit about the symbol management that we integrated. So let's browse functions, go up, and you can see that I loaded the symbols of the kernel, I loaded the symbols of the receiver task and of the sender task. And if you go down again, and let's see for symbol main, and we see that we have two symbols main here, because we have two applications. I can double click on the first one, I can double click on the second one, and you can see that I can view into the main function of the sender application and into the main function of the receiver application, and both at the same time. Of course, can set breakpoints, look into global variables and all that stuff at the same time. So there's an easy way to handle the symbols and to navigate through all the symbols. So let's have a closer look into the receiver application. The receiver application has only one thread, and currently the sender application runs, but still we can look into the stack frame of the receiver thread. Let's condense this, and you can see that the receiver, of course, started at main, then called some subroutine, and it called VMQ port read, and that's where it's currently waiting for. It waits for the reading the Q port, and if we add the caller and double click on this one, we are right at the location, switch the mode, at the location where the thread currently waits for. So setting a breakpoint on the next line, close all the intermediate windows and say go. And we're holding at the breakpoint right when the thread is back on the scheduling and on the breakpoint. And of course, now we are able to start debugging on this thread. Of course, you can do the same here on the Cortex R side. At the same time, you have to use the right click and display stack frame. And also you have the stack frame here. And you can see here we have again the main, and the task is waiting for Q port right. Switching on the caller, double click, Q port right, setting a breakpoint on the next line. Let's switch the mode and say go. And we are halting at this as soon as the process is back here. So it's the same look and feel and the same debugging on PikeOS for MPU as for PikeOS. This is mainly about debugging on both sides simultaneously, as I showed you, but also interesting is the trace. So let's open the trace configuration and initialize the trace to have a trace recording, and I will reduce the trace size to have a quicker evaluation. And let's do a go. I still have a breakpoint. Yes, I don't want to have that one. And do an init again and do a go again. And you can see that we are recording the program flow right now on both sides. Let's halt it again. And by doing this, now we have a complete recording of the program flow. This is the recorded object code. And out of this, we can do some nice measurements. For example, task runtime measurements. So you can show which task was running when, which gives a nice overview of your system. It's a nice view, but more interesting is probably the numerical analysis, where you can see which task cost the most runtime, and you can really see here that, well, it's almost even between the receiver and the sender. And not only on task level, you can do this also on functional level. So first as a timing, so that you can really see when which function was running and which function called which other function, and do a comprehensive analysis on that. Of course, the same function runtime as statistical analysis so that you can see which function took the most time, and not only that, also an analysis of the function call hierarchy within the trace. And as we recorded the program flow, we can do the code coverage. So let's list the modules in our system, scroll down to the applications, and add the contents of the trace memory. And as you can see, it showed we added some coverage, for example, here in the sender, and the write pattern was covered only partial, and we can also resolve this to source lines. Double click on it and you can see which lines were covered. Here's the write pattern, and you can see that almost everything is covered. Okay, only partial this line. And of course, the assert is for errors. We don't have errors now in this recording. So the assert was not covered by the code coverage, but everything else of this function was. So I have a quick view of the code coverage. Of course, you can also export this into a nice report, HTML report, so that you can include this into your documentation. So this was the Cortex-A side. Of course, you can do the same on the Cortex-R side. So again, show the timing of functions. I filtered out the kernel function in this case to have a better overview, and also do the statistical analysis. So to see which function costs the most runtime and all that stuff. So it's equally to the Cortex-A side, it's exactly the same behavior. And of course, the same for the code coverage here. Again, list the modules, add the current recording, scroll down to our application, and you can see that the main function was covered partially here, and you can easily see which line was covered by the code coverage, by the current trace recording. So we recorded the trace on both sides, I said. So let's see, let's have once again a look at the runtime of the tasks on the Cortex-A side and on the runtime of the functions on the Cortex-R side. Now, the nice thing is that you can synchronize both traces. If I click onto the one trace, you can see that a marker is set on the other side, and also vice versa. So you can really see which events on one side caused which events on the other side. And for example, let's go into the QPort read function here, and let's go to the end of the QPort read functions and scroll a little bit out so that we can see a little bit more on the other side. And so this is where the QPort read actually, oh, sorry, it should be the right. It should be the end of the right, not the, yes. So I wanted to have that one, the end of the QPort write. And if you scroll out, this is where the PikeOS for MPU sends out some data, and now you can actually scroll a little bit and measure the time when the Cortex-R sent something to Cortex-A, and this happened in 617 nanoseconds. So this way you can really measure out your system by synchronizing the tracing and exactly see how long your application took, and how long a message took from one side to the other side. So this shows that TRACE32 with PikeOS and PikeOS for MPU really works fine on heterogeneous and helps you out in debugging the heterogeneous system of PikeOS, and to not only find your bugs, but also do the certification for your levels of certification that you do have. And with this, I would like to hand back to Amani.
So thank you, Rudolf. So now let's take a moment to summarize and reflect on the key takeaways for today. With safe and secure PikeOS and PikeOS for MPU, and with the support of TRACE32 tools, developers have complete solutions at their disposal to address challenges in the complex landscape of heterogeneous SoCs. Safety and security also are paramount, and here we have PikeOS, which adheres to the highest safety and security standards, including DO 178C. And this ensures that our solutions are both reliable and compliant with industry benchmarks. With TRACE32 tools, developers experience a fluid debugging and tracing process for both PikeOS and PikeOS for MPU, ensuring efficient troubleshooting. And TRACE32 isn't just about debugging. It is a comprehensive suite that facilitates tasks like concurrent access, variable inspection, breakpoints management, and in-depth performance analysis across PikeOS variants. Also, we have addressed the multi-core topic. And here PikeOS for MPU comes as a perfect complement to the classic PikeOS, especially designed to harness the capabilities of asymmetric multi-core setups. And you know what's the best part? TRACE32 also supports them all. And it's worth noting that a single TRACE32 hardware setup is all it takes to debug both PikeOS variants. Visualization also helps comprehension, and TRACE32 graphical timing chart offer a flexible way to observe and understand timing behaviors for both PikeOS and PikeOS for MPU. And at the end, our collaboration helps a lot to make a more swift certification process, and this is allowing developers to achieve their certification goals more efficiently.
Yeah, thank you very much, Amani. Thank you very much, Rudolf. Very nice presentations. Also, the demo pretty much shows the advantages of both solutions for the customers. So if you have further questions to SYSGO or Lauterbach, you see the contacts here. Please feel free to get in contact with us. And please also join us on our social media channels, both from Lauterbach and SYSGO. Have a nice day wherever you are. Thank you so much.